Section 15.6 Applications of Equilibrium Constants. We have seen that the magnitude of K indicates the extent to which a reaction will proceed. If K is very large, the equilibrium mixture will contain mostly substances on the product side of the equation. That is, the reaction will tend to proceed far to the right. If K is very small, that is, much less than 1, the equilibrium mixture will contain mainly reactants. The equilibrium constant also allows us to 1. Predict the direction in which the reaction mixture will proceed to achieve equilibrium, and 2. Calculate concentrations of reactants and products when equilibrium has been reached. Predicting the direction of reaction. For the formation of ammonia from nitrogen and hydrogen, equation 15.6, where the equilibrium constant is 0.105 at 472 Celsius, suppose that we place a mixture of 2 moles of hydrogen, 1 mole of nitrogen, and 2 moles of ammonia in a 1-liter container at 472 Celsius. How will the mixture react to reach equilibrium? Will nitrogen and hydrogen react to form more ammonia, or will ammonia decompose to form nitrogen and hydrogen? To answer this question, we can substitute the starting concentrations of nitrogen, hydrogen, and ammonia into the equilibrium constant expression and compare its values to the equilibrium constant. So K sub C equals 0.105, whereas at present it's 0.0500. To reach equilibrium, the quotient will need to decrease from the starting value of 0.500 to the equilibrium value of 0.105. Because the system is closed, this change can happen only if the concentration of ammonia decreases and the concentrations of nitrogen and hydrogen increase. Thus, the reaction proceeds towards equilibrium by forming nitrogen and hydrogen gases from ammonia. That is, the reaction proceeds from the right to the left. The approach we have illustrated can be formalized by defining a quantity called the reaction quotient. The reaction quotient, Q, is a number obtained by substituting reactant and product concentrations or partial pressures at any point during a reaction into an equilibrium constant expression. Therefore, the general equation, the reaction quotient, is defined as A is related quantity. Q sub P can be written for any reaction that involves gases by using partial pressures instead of concentrations. Although we use the equilibrium constant expression to calculate the reaction quotient, the concentrations that we are not restricted to the equilibrium state. Thus, in our earlier sample, when we substitute the starting concentration into the equilibrium constant expression, we obtained Q sub C equals 0.5, whereas K sub C equals 0.105. The equilibrium constant has only one value at each temperature. The reaction quotient, however, varies as the reaction proceeds. To determine the direction in which the reaction will proceed to achieve equilibrium, we compare the values of Q sub C and K sub C, or Q sub P and K sub P. 3 possible situations arise. If Q is equal to K, then the reaction quotient will be equal to the equilibrium constant only if the system is already at equilibrium. If Q is greater than K, the concentration of the products is too large, that of the reactants is too small. Thus, substances on the right side will react to form substances on the left, and the reaction moves from right to left in approaching equilibrium. When Q is less than K, the concentration of products is too small, and that of the reactants too large. Thus, the reactions will achieve equilibrium by forming more products that moves from left to right. These relationships are summarized in Figure 15.9. Figure 15.9. Predicting the direction of a reaction by comparing Q and K. The relative magnitudes of reaction quotient Q and equilibrium constant K indicate how the reaction mixture changes as it moves towards equilibrium. If Q is smaller than K, the reaction proceeds from left to right until Q equals K. When Q equals K, the reaction is at equilibrium and has no tendency to change. If Q is larger than K, the reaction proceeds from right to left until Q equals K. Calculating equilibrium concentrations. Chemists frequently need to calculate the amounts of reactants and products present at equilibrium. Our approach in solving problems of this type is similar to the one we use for evaluating equilibrium constants. We tabulate the initial concentrations or partial pressures, the changes therein, and the final equilibrium concentrations or partial pressures. Usually, we end up using the equilibrium constant expression to derive an equation that must be solved for an unknown quantity, as demonstrated in sample exercise 1511. In many situations, we still know the value of the equilibrium constant and the initial amounts of all species. We must then solve for the equilibrium amounts. Solving for this type of problem usually entails treating the change in concentration as a variable. The stoichiometry of the reaction gives us a relationship between the changes in the amounts of all the reactants and products, as illustrated in sample exercise 1512.